Okay, so the beginning ones are the backgrounds, because information theory may be slightly unfamiliar to people, but the aim is trying to say that you don't have to be, rocket science superstars. There's lots of intuitions behind things, and let's try to understand that way. So motivation, why do we want this topic? And then we have formulating what do we mean by efficient coding, to be precise, yeah, and this way is very helpful. And then we apply this principle to understand things of interest. Yeah, we say, okay, how do we understand receptive field? What if I'm a neurobiologist? What if I'm just a psychologist? Or what if I'm a computational person? We can all have our own needs, and hopefully can we address them? Okay, and so then we apply these principles to understand the receptive fields. And this is, first of all, we apply these principles to just some examples: contrast, color, space, coding, and so on. And then there's a huge things. Okay, let me see, get this pointer. There is a big body of things. They share the same idea, the receptive field transform. So it's center surround receptive fields, color selectivity, orientation selectivity, motion selectivity, and so on. Apply these principles to these various receptive fields. And so that's how we, first of all, we derive, do we have an analytical solution to this optimization for problem? Optimize, trying to make things efficient. What do we mean by efficiency? Make it efficient, okay? And then we try to digest it, because in the beginning it may be very dry, maybe mathematically dry, yeah? Digest it with a simple example, which is just two-dimensional problem of two eyes, left eye input, right eye input, and it's easy to digest. So in this case, that means if you feel lost in mathematics, there's not a problem, because we can digest it, then you will not get lost afterwards. And then use this intuition of digesting to apply to space, color, and time coding. Okay, and as a gist, again, using intuition. And then we try to apply this, because by then we already have this analytical solution. Very nice. So therefore we have a recipe. We apply this to understand the spatial receptive fields in the retina. Okay, and how can we derive, then we can derive the center surround receptive fields in the retina according to the input statistics of natural scenes. And then we can apply it to tempo coding. So for the spatial coding, tempo coding are tempo filters. So for example, your neurons can be sustained response, transient response. What does that mean by sustained response? It's basically some kind of a particular filter form, and that's tempo coding. And sometimes people even talk about these transient responses as predictive coding. But those predictive is encoding, not decoding, okay? And you can apply it to color coding. So how do you understand your selectivity to chrominance and luminance and chromatic channels? And how do you understand adaptation? Okay, and then we can say, okay, you separate space, time, and color. Can we combine it together? Okay, let's have an example of combining space and color. So for instance, in retina, you will have receptive field that's not only tuned, it's a center surround receptive field. They could have center red and surround green. So center excited red and surround inhibitory green. How does that come about? Okay, so for example, and you can also then, now how about spatial receptive field in V1? Obviously, it's different from retina. What does that mean? Can we also understand from these principles or not? Yeah, and then now can we couple space and color in V1, which is obviously different from in the retina, because in V1 we have double opponent neurons. Double opponent, double means space and color double. And in retina, it's single opponent neuron. Why is it different? Yeah, things like that. And how about we do not couple space with color, but space with ocularity. Ocularity is the left eye and right eye. So space is, where things are in visual space, and eye is which eye is input. Put these things together, you not only have ocular dominance, you also have disparity tuning. Yeah, and so how does disparity tuning come out from this? And then you can also couple space with time. Previously, we only have space, we only have time. But if you put together, that's motion. okay, because motion is change in space across time, okay? So therefore you will get motion direction selectivity from that. And then you can say, okay, shall we couple everything, not just space with time, space with color, space with ocularity, couple everything, space, time, color, and ocularity. Is it possible? Is it not possible? Is it only limited coupling? Is there some constraint and things like that? So that's so these are the 44 videos, more or less in this kind of a skeleton. And this, within this blue box is, we have come to a particular analytical solution that has some, assuming receptive fields are linear, assuming, not assuming, approximating signal as Gaussian in a sense that, but the natural things are not Gaussian. So therefore, let's look at the alternative when they are not having to assume this, okay? When not having to assume this, people have probably heard about these numerical. Unfortunately, by doing that, you no longer have analytical solution, but nevertheless, you can still do numerical simulations and you can get rid of some of the approximation and assumptions, and such as sparse coding and so on. They are in the same spirit as the efficient coding. Can we see something more, or do we see the same thing, or do we see the different things? So that's the question we can ask in this video. And then we can ask, that's a very small asking and answer, you know, all these is saying why, how should the efficient coding be? But no. Why should the efficient coding be? How do you develop it in, you know, when a baby is born, when you know, you expose before eye opening, after over? How can the neuron wired up to such efficient coding representations? So that's a very short section on that. And the last is trying to see where is the limit of efficient coding. Can we really understand all the way from retina to V1 to V2 to V3, V4, IT, and so on? That would be really nice, because that was in the original spirit of Barlow. Horace Barlow was the one behind this efficient coding idea. The idea is when you get efficient, things become independent components. And in the end, if we recognize an object, a face, a tree, and so on, these are independent components. And maybe this can be achieved by efficient coding, or maybe not. Let's see, can we do that? Yeah. Okay, there's still 4 people. Let me admit from the waiting room. Okay, so admit. Okay. Sorry, people in the waiting room. I'm kind of talking, so I may not notice you promptly. Okay, so that's more or less the 44 videos, and then let's also, okay, what is it? Okay, the formulation is just in the beginning, say, what do we mean by efficient coding? It's the idea is we have the signal S and noise N and comes in. They have particular input statistics. So what does that mean by input statistics? That means the signal follows particular probability distribution. Okay, the signal could be multidimensional. For instance, if you have an image which has 1 million pixels, then the signal is a 1 million dimensional distribution. Okay, it's a really, so that's what it means, an input statistic. People talk about natural seeing and non-natural seeing, means the probability is following. Natural seeing has one particular probability and non-natural has a different probability, okay? And from this, you say, how can I transform it by this K? K is a function which takes the input to response. How can I transform from an input, which is photoreceptors as a function of space and time, and the cone type, red, green, blue type, and as a function of which eye, left eye and right eye, transform it into neural responses. O stands for output. Transform it by receptive field, by input response function, contrast response function, whatever you like to do, to capture input selectivities and sensitivity. That's the neurobiological terms. In engineering terms, you could say to capture, like, you know, filtering properties. You know, people probably heard about filters, kernels, and the K is standing from the kernel. And then you get this response O in, let's say, retinal ganglion cells, V1 cell. They contain information about input. So that's what that means. They are encoding information by their responses. Efficient coding answers what should this transformation K be and why. Y is for efficiency, for information, okay? And so this is what they formulate, that the K should be such that it minimizes objective function, and it minimizes this. What does it minimize? It minimizes the neural cost. Cost could be in the spikes, in firing, in the wiring, lots of things you can do. And while maximizing the mutual information between O, which is the response of the neuron, and input S signal, the mutual information. So therefore, in Word, it says efficient coding is like data compression, okay? Because when you compress data, you don't have to have, let's say you store it, don't need as much memory. You can imagine the memory storage is the neural cost. You can also say neural firing is a particular representation. Memory in your computer is another. So that's the data compression. Data compression means you want to have the data compression. Hopefully you can still unzip the data. Okay, you can still decompress and get all information. That means that most of you want to extract as much information. So if the information is not really extracted, it's more like data deletion. Yeah, it's not data compression. And in visual system, in the beginning bit, before the attentional bottleneck comes in, it's more or less lossless. But you can say loss a little bit and not completely lost. So essentially, most of the information hopefully is extracted. And this has been proposed many years ago. And then additional researchers apply this into particular formulations so they can make it more precise. In the beginning, it's more like in concept. But this concept is already very good. Okay, it's already very good. And if you can write it in precise medical forms, then you can be more precise, can make a predictive power a bit more powerful. Okay, and so a key point is this. A key point is this K will depend on the input probability distribution. Why? Because the neural cost, eventually, how do you fire or not fire depends on what is your input statistics. As well as mutual information. If you look at the videos, you always see that mutual information is a probabilistic term, okay? It depends on your probability distribution. So therefore, this whole thing depends on input statistics. So if you change input statistics, you will change your receptive field K, okay? So therefore, it says that different feature dimensions, whether it's input contrast, whether it's input distribution in space, input distribution in time, color, or eye of origin, they will be characterized by different probability distributions. And because of that, if you want to optimize this objective function, you will get different receptive fields. So therefore, you can understand receptive field in space, time, color, and everything by a same principle, except just by give different input statistics. That's the power of when people say, can we have first principles? Can we have a unifying principle? The first principle, unifying principle, means that lots of things, one principle. That's the idea, okay? So lots of things, space, color, eye, origins, and one principle. And then you say, how can you get different result? One principle. Or different result is because you give different initial conditions, you give different environments, you give different input dimensions. So input dimension could be in space, 1,000 pixels or 10 pixels or 1 million pixels, depending on what animal it is, yeah? So we humans have 1 million pixels, maybe other animals not so many, and so on. Maybe you're living underwater. In the water environment, the color statistics different because maybe the blue light is filtered more or filtered less, and so therefore you have different probability distribution of your color signals compared to animals living above water, and so on. So therefore, by giving different input statistics, you will get all these diversity. Okay, so therefore, one principle, diversity of results. That's something it's very satisfying for computational neuroscientists, as well as for experimental biologists, because you can link your finding in your particular animal, this species, with another finding in a different animal, different species in different situation. That's very nice. And so that's how it comes out. Different animal species have different habitat. So therefore, let me see if there's other people in the way. Therefore, they will also have different statistics. And sometimes you may even have different lambda. Now, what is this lambda? Lambda is characterizing the trade-off between the good and bad. Because cost is expensive, bad, you want to minimize it, okay? Mutual information is the good thing, you want to have it. But there's also, nothing is free, yeah? You got to pay for it, yeah? So you pay the cost in order to get it. And how much you are willing to pay is by this lambda. So different animal species may have a different affordance. Yeah, so I can afford to pay more and another species can afford to pay less and so on. So that can also enter, and therefore you can also, because of that, have different receptive fields for different animals. So different animal is not because they have, not only just because they have different habitats, like underwater, overwater, how many pixels in your images and so on. And also even within the same animal, let's say you humans, you can also change. The idea is, you may be in indoor environment versus outdoor environment. Now, what does that mean? Your probability distribution in indoor environment, outdoor environment will also change. So for instance, in indoor environment, the amplitude of your signal is higher or lower, okay? And then the signal noise is high because this probability is with respect to the noise, okay? And so you can always kind of normalize your signal with respect to the noise. And so that can say, how can the so the animal, you have adaptation, your color perception can be adapted. In fact, partly is because your receptive field is adapting. And you can also have the receptive field, for instance, center surround receptive field in the retina. It can certainly become, the center become bigger, surround become weaker when you go to dimmer environment. That comes out as a solution for the same equation, except you're putting a different input statistics. Yeah, so that can come out. And so that's the highlight. And so these are the key points. In fact, because of these key points, that makes this theory very predictive. That means it can have predictive power because you say, hey, one thing I like to use this theory is to understand the existing receptive fields. I say, understand is very satisfying as a student, as a researcher. Now I understand the past data. Now, can you then understand the data that has never been observed? That's called predicting something. And that will really put the theory into testable, whether you can falsify a theory or you can test it. You say, well, everybody has already looked at the monkey's receptive field and cat's receptive field. I don't have anything that's not done. Well, you can get something that's not done. What do? You change the input environment to the monkey, such that this environment, for instance, you can say, how about I change the natural scene correlations, spatial correlation? The monkey have never seen it. Then if this theory is correct, you change the input statistics, the receptive field should change. It can precisely predict how should it change. Then you can do experiment and test it. Okay, so that's the idea. So that makes this theory very falsifiable. And we have some of these examples in one of the video clips, testing it in ocular dominance coding. Yeah, and so that will probably see one of those. Anyway, these are one of the key points. And therefore, you can answer all these questions. You plug this in, you can answer all these questions. Why should contrast sensitivity be so? Why should the receptive field have similar surround receptive field? Why should the receptive field increase size in dim light? It's all because of this. Now we find, because for instance, why should receptive field increase size in dim light? Because in dim light, the input statistics change and therefore the resolution change. Why should contrast sensitivity be so? Because you have an input distribution of input sensitivity. Given that, then the contrast response should be such that minimize that, okay, so on and so forth. How does the ocular dominance column of V1 neurons depend on developmental conditions? Or for instance, depend on which animals. For instance, squirrel monkeys have their two eyes very close, and hammerhead shark with their eyes very far away from each other. Now, when the eyes close and eye far away from each other, that means you have different input correlations. Yeah, the closed eyes, the inputs are very similar, so strong correlation, and fast eyes, two eyes are very different, and the different correlations. The correlation input statistics is one of the characters of input statistics, and then you can plug it in and get your different solution. Okay, so that's the idea. The visual input statistic determines the coding, determining the receptive field. That's the idea. Okay, so I just want to have a little bit of feedback from you. Do you think I'm talking too fast, too slow? You give me a nod and shake your head and so on. Yeah, everything okay? Yeah, wonderful. Thank you very much for your feedback. Thank you. Yeah. Okay, so let's now. So for instance, input statistics of probability distribution could be input contrast. You get a contrast response function. Probability distribution of object on a retina due to eye movement, because you move your eyes and to put object in different locations. Then you can then derive what should be the photoreceptor density on the retina. You can derive that from that, okay? And then if it's what is the distribution of color spectrum in your environment, then you can just derive what kind of cones. Should I have red cone, green cone only, or blue cone, red cone? Why some animals have only 2 cones and other animals have 4 cones, and so on and so forth. Yeah. And how about correlation between 2 eyes? Then you can have the stereo coding. Remember, I talked about hammerhead shark and squirrel monkey versus cats, and so on. And how about the spatial correlations between the pixels? Because we have these spatial correlations, which is often reflected in the power spectrum of natural things. People probably heard about like a natural things have this colored, 1 over k squared, the power spectrum. This power spectrum is a function of spatial correlations. And from that, then you can solve this equation and get your center surrounding the fields. Yeah. And then you can also say, dim light and bright light, and then how does the field should change. And you can have more examples such as, how about temporal correlations, yeah? And from the temporal correlations, depending on the signal noise, you could get temporal filters, get sustained and transient neural responses, and so on. And correlation between the red cone and green cone. For instance, red and green cone, they are having most preferred color spectrum very close to each other. So you can imagine the red and green cone have much stronger correlation between their responses compared to a red cone and blue cone, because red cone and blue cone, their spectrum are further away. The most preferred spectrum is further away, so the correlation is less. What does that mean? Does that mean that in the retina, coding between red and green is different from coding between red and blue? That should be the intuition. Then using this intuition, you can check whether the analytical solution match your intuition. This is always a good idea because, math alone is too abstract. We need to digest it. So whenever your math result, you also want to say, does that make sense to you? Okay, so that's important. Or you can talk about, how about we also have joint distribution? It's not just distribution, spatial distribution of the pixels, okay, but also color distribution. But what about the joint distribution between space and color? Then you will have these kind of a spatial chromatic receptive fields. And what if you change color statistics? For instance, if you go from the daylight where you have the sunlight shining, and suddenly you go to a disco environment where people have very strange neon light, what does that mean? That's changing input statistics. Then your receptive field in the eyes will change. And then suddenly some colors don't look quite the same to you. Maybe you have a beautiful sweater you wear into the disco. By the time you go to the disco, you realize that the beautiful sweater color maybe not so ideal as you thought, or something like that. No, this is because of color adaptation. Yeah, now you can understand it that way. And you can also talk about, how about joint probability distribution in space and eye of origin. Then you get disparity tuning, and you can also change these probability distributions, the correlation between left and right eyes. You say, how do I change? I have my eyes like that. How do I change that? Well, these days you can use stereo goggles, wear the goggles in like 3D cinemas, and you just artificially give people look at these things with different input to the eyes that's no longer as correlated or more correlated than in your natural things. You just distorted its input environment. Then its ocular dominance coding will change, and so on and so forth. It will lead to perceptual consequences, such including disparity tuning and disparity sensitivity. And this can actually be behaviorally measured, and recently is measured by some research groups. So that can go from the encoding statistics to perception with the help of this computational understanding, starting from Horace-Bowler's principle. Then we use the tools and to derive that. And so a very useful case is sometimes, you can have this intuition, but sometimes you want to be precise to have analytical solution. So a useful case is, imagine your neural course is in fact in terms of the neurons firing. Remember, the output is the neurons response O, okay? And O1, O2, O3 means neuron number 1, neuron number 2, neuron number 3. Okay, so all these I is different neurons, all different neurons at different times. So you add them, they are squared. It's kind of like a power, yeah, variance. Variance often is associated in engineering like dynamic range. Okay, if it's a zero mean Gaussian, it's associated with power. So you can imagine dynamic range engineering and power, they are all neural cost. Yeah. So if the neural cost is instead of this, and people who are familiar with linear algebra and a lot of things, you know when things are quadratic, it's easy to solve. Okay. It's easy. So that there is some kind of so therefore this is like, if we do it quadratic, it's easy to solve. Okay. And then you put it in, then this becomes that. And so that's the first thing. Secondly, let's assume that your the K transformation is linear. So that in particular for different pixels, S, J, and so on, you just have a matrix, linear matrix come to the output. So that means linear receptive field. Okay. So this J can mean different pixels, different eyes, different cones, different time. Anything you want. So this J, depending on whether you look at the spatial coding, color coding of different J's, and this I is different alpha neurons at different time instances and so on, okay? And then you have a linear coding. Now we have to keep in mind that linear coding may not be exact, because this is more applicable in retina. Retina is almost linear until you come to the stage where you have to transform into spikes. But before you transform spikes, retina actually has no spikes until the retinal ganglion cell output. So keep that and simple cells in V1, you can say, well, actually it has a rectifier, okay, before linear. And so therefore keep that in mind. You can imagine that this linear encoding is like two rectified on-off cell put together. It's a linear cell, okay? So with that, and also giving the assumption that signals are almost Gaussian, you can also ask yourself, is this a good assumption or bad assumption? This is one of the videos. In the end, we actually trying to quantify whether it's a good assumption or bad assumption, okay? But anyway, once you have this assumption, it gives you a lot of power. You can actually solve this analytically. Now, the power of solving this that enables us to go beyond the qualitative concept that Paul Sparrow originally proposed, that increases the theoretical predictive power. So in particular, we presented in a textbook this analytical solution, more or less have three conceptual steps. One is just do the principal component analysis. Everybody is comfortable with that, PCA. Just use the signal correlation, okay? Because now in this situation, if things are Gaussian, you can characterize this probability distribution by the correlation matrix of the signal. So if your signal is just two-dimensional, left eye, right eye, this is a 2x2 matrix. If your signal is 1 million pixels, this is 1 million by 1 million correlation matrix. Correlation everybody can do, including experimentalists. You can have two neurons correlate, two pixels correlate. So all you need is this correlation matrix. Given the correlation matrix, you can do PCA and you can get that. That's the first step in that. Now, in the neural system, you don't actually do this first step, second step, third step, okay? In neural system, you can do it in one step, which is a multiplication of 3 steps to get together, cascade. Or you can do it in 10 steps. It doesn't matter, because every step is a linear operation. You can combine the 10-step linear operation as one operation, or you can separate it into n as you like. As we know in retina, we go from photoreceptors to bipolar to horizontal to emequantal. So you can do many, many steps if you like. Yeah, it doesn't matter. And conceptually, it's these 3 steps, okay? And then you can ask the question, why do retina have all these different steps? Well, because remember that if you change your input statistics, the solution K will change. And how does it change? How does it adapt? If you adapt, you might have to have a lot of these hardware steps in between in order to make the retina very flexible to change, yeah? And so you have that. And then in the, so in the end, you also have multiplexing. The multiplexing, this is the last step, is free to choose. This basically says that this optimization function to minimize this solution has many, many, many solutions. In mathematics, it's called solution is degenerate. It's many possible solutions. And for those of you who are comfortable with like a PCA, decorrelation, decorrelation solution, after decorrelation, you can rotate it still. So that's the idea. You have lots of solutions within a particular solution space. And then you may then choose it. Another thing is, this is the gain control, which also has a particular formula. There's a recipe in the book that you can follow. And choosing this can make you do additional things, so that you may put these additional things as part of the objective function if you like. But the additional thing could be like, I want to have all my receptive field have the same shape. Okay, let's say all my retinal ganglion cell, I want them to have all the same shape for different neurons, except it's shifted in space. Receptive field center shifted everything. So you can impose that, so to nail down this freedom. You can also impose other things, such as I want things to have translation and scale invariance. I want wavelet coding or some kind of things. And you can impose that by choosing that. Okay, then you can get the V1 receptive field. And so that's more or less a recipe. And with this recipe, that's more or less within this box. Okay, this box is literally, we now have a recipe. Okay, and in the first two videos, I just showed you how this recipe is derived. And please do not get discouraged in these videos when you feel like it's so dry mathematics. Don't get discouraged, because we will then use this 2x2 matrix in stereo coding, where you only have two eyes, left and right eyes, to digest it. So even if you feel a little bit lost, here we digest it. That's why it's a many videos, 1, 2, 3, 4, 5, 6, 7, 8 videos for you to digest. And because it's a low dimensional space, only left eye and right eye, and you will really digest, what do I mean by the first step, what do I mean by the second step, and what do I mean by the third step. And with this digestion, you can apply to everything else, okay? Because qualitatively, they're the same thing. So there's a 2x2 matrix for visual input to the two eyes. For spatial coding, 2x2 matrix, we can write n by n matrix, because now you have n input pixels as a function of space. Yeah, n is the spatial pixels. And you can also have temporal coding, n time points. Yeah, so you get n time points, except there's something additional to spatial coding, because the receptive field has to be causal. Okay, it cannot be acausal, because the response O depends only on the past input signal S, not in the future. And that causality is not required in spatial coding, because the response of this neuron can depend on input to the left of it, and photoreceptor to the left of it, and the right of it. Doesn't matter. Okay, but in time, any response of a neuron can only depend on the input in the past and not in the future. And so this will also constrain what kind of a U could be. And fortunately, we have the freedom to do that. So this can do. And then in color coding, you can then go into a lower dimensional space, because you have a red, green, blue color, for instance, for the monkeys. But you can also have, let's say, another animal dichromatic, yeah? And then it's only 2x2 matrix. Or you can have another animal, 4 different cones, 4x4 matrix. So we have done 2x2 matrix. We have done n by n matrix, coming back to 3x3 matrix. It should feel comfortable, yeah? So that's the idea. You get that, and you can get also this luminance and chromatic. In terms of the luminance, chromatic, they are just different PCAs, okay? The luminance channel is the first PCA. Remember, this is the PCA. Okay, so the luminance channel is the first PCA, and the two next PCA, the two chromatic channel. One is red-green chromatic channel, is the second PCA. Blue-yellow chromatic channel is the third PCA, yeah? So another person in the waiting room, let me get him over. Him or her. Okay, where is it? How can I just get the message? Yeah. There's okay, admit. Okay. Sorry, I didn't see you in the waiting room until now. Yeah. So, and then we can continue, and you can also say that, okay, what if I couple space with color? Yeah. And so therefore color is 3-dimensional, space is n-dimensional. So now you have 3n by 3n matrix. Don't get scared, because 3 by 3n by 3n, how can we understand from 3 by 3 matrix and n by n matrix? They can, in fact, turns out it's tensor product. And if you are doing TensorFlow, tensor product is much easier than TensorFlow, so don't worry about it. But even if you're not doing TensorFlow, so that's how we're trying to, hopefully the video can help you with that. And then you can talk about, okay, now we also have spatial coding, but in V1, We have already done spatial coding in the retina. What's the difference? Yeah. Now remember, we have this U matrix has a little bit of freedom to choose. Okay, and so you just choose a U matrix for V1 is multi-scale coding. However, we have a big monster here. Okay, what is the monster? V1 turns out is over complete representation. And this over complete representation is in conflict with efficient coding because V1 has 100 times as many neurons as retina. So the cost dramatically increased. Yeah, so this is a little bit of a problem there, and we currently, we continue, we just march on. Yeah, march on, first of all, temporarily ignoring and postponing this issue for later. Yeah, so pretend that V1 doesn't have 100 times as many neurons, just as if it's not the case, and let's do that. And then you're trying to understand how the V1 can have, how could we change this U matrix such that neurons are, receptive fields are not copies of each other, just tidying up the space, but some oriented this way or some oriented that way. Some prefer low spatial frequency, some prefer high spatial frequency, and so on. Yeah, okay. And then you can also have, how about we not couple space and color in V1? It's different from couple space and color in the retina because of these multi-scale coding, yeah? And you can also, how about couple space and ocularity? Now, V1 does have something that retina doesn't have. So we have space, time, and color already in the retina, okay? Space, time, color already in there. But there is no stereo vision on the retina because the retina, one eye is only one eye, not the other eye. The two eyes are only combined in the primary visual cortex. So therefore, when we talk about this stereo coding and coupling stereo with space is something that's kind of still left undone until we can do it in V1. Yeah, and so that's quite interesting. Then you get to this disparity tuning, and we haven't yet talked about space-time coupling. We could already talk about it in retina, but we kind of delay it to talk about it later here. So space and time, so that's motion, right? Motion is change in space and time. And then you have nx dimensional space and t dimensional time times nx and t matrix. So it's a very high dimensional matrix, okay? But no fear, because we have this recipe. Just plug in the recipe and do it. So with the recipe, we can do all these, no problem. And then you say, okay, each time you're just coupling two things, space with color, space with color, space with ocularity, space with time. How about put them all together? Space, time, color, stereo, all of them. Okay, are we allowed? Well, this recipe allows you to do them all. But then you say, does the visual system actually do it? Okay, then you find that, yes, in V1, you have some cells tuned to both space and time, right? Motion direction selectivity is tuned to both space and time. You also have both space and color, cells tuned to orientation and color and so on, and cell tuned to, monocular cell, binocular cell, and all these kind of things. But the more you seldom have cells tuned to three different dimensions, okay? The reason is here we have this gain control. Again, in the recipe, the gain control has a precise prescription. And this gain control, well, when the gain is 0, then you don't have that neuron, okay? 0 gain, that means it just doesn't have any sensitivities left. And so therefore you can understand why in V1, some neurons exist and some other neurons don't exist. So neurons tuned to one feature dimension, yes, they do exist. 2 feature dimension, yeah, they still exist, depending on which 2 feature, okay? Then 3 feature dimension, well, difficult, and so on and so forth, because of this gain control, yeah? It's very, and then, okay, all of this is within this blue box where we can have this analytical power, just apply them, okay? And all of these steps, you can just do that. However, you will still keep in mind, look, there is a conflict. This conflict is not resolved. Is that because this conflict, because we have this simplification of linear receptive field, approximation of infostasis as if it's Gaussian, but actually natural things are non-Gaussian, and so on, okay? And so therefore, we can now look, what if we abandon this simplification? So you can use these numerical simulations to abandon these simplifications. And turns out even doing that, now you can have sparse coding and many other things. So you can do gradient descent to get your best coding, but not use your analytical solution to do that, and so on. But this conflict is not resolved. Yeah, the reason is this conflict is so fundamental. Neural cost. It's not something you can resolve by modifying the objective function a little bit. You know, how about we don't make the objective function, which is the dynamic range, but you know, something else. Unless you modify it qualitatively, completely modify, you can't, because this conflict is too fundamental. But if you fundamentally modify, then it's no longer efficient coding. Do you see what I mean? So it's fundamentally in the root of efficient coding. That's why it's not resolved. And that's why we kind of come to an understanding that perhaps the efficient coding does not go all the way as what Horace Barlow had envisioned that it could go. But that's not necessarily a bad news, okay? The reason is every time you come to a limit when you have problems, it's actually an opportunity. And so we can discuss what opportunities to open up, because often when you have a problem, you discover something new, yeah? So that's the idea. And so this is more or less the first, first session. Everybody's very quiet. I wonder whether there's a way to, you know, have people just unmute yourself and shout something. We are 3 minutes to the break, but I'm happy, I think, to not, you know, I just hang around. We can talk and through the break and start to the next hour for the second session for Q&A, but we can just chat. Please just unmute yourself. We don't have like a massive amount of people, so I actually prefer you can, well, let's just self-organize and play by ear, that you can just shout your questions at me, yeah? Would you please? Or comments, or things like that, yeah? Yeah, that's more or less it. Hi, Curtis, how about you? I like to,
okay. Hi, good to see you. I had one question about the assumption of Gaussian inputs. Because in natural images, I think I remember it being said that the distributions of pixel luminance are quite non-Gaussian. They have a high kurtosis, heavy tail. Is that a minor issue here, or does that have...
It is the issue that's addressed in one of the in one of the video. Turns out that if you measure by kurtosis, where is it? I'm sorry. So this is our one of the video actually addressed that issue. Turns out if you measure by kurtosis, it is huge difference. It's as if it's a very poor Gaussian approximation. However, if you do it by bits, entropy, that's how you measure for mutual information, then it's a very good approximation. Turns out that higher order statistics only composed of 3% of the redundancy, while the lower order statistics is 50% of redundancy, depending on how many bits of information you use as pixel depth. So they basically are very little. So let me just go to this. Yeah, this is one of the, yeah. Maybe we can share screen into one of those videos. So this is the video in it, and let's go to the idea of one of the last problem with understanding V1 from problem with understanding V1. I can go somewhere. Okay, so this is the idea.
Quantify this.
Yeah, so this is exactly where we quantify. So you have a visual image called natural or not natural, and this is after you whiten. And whiten become this. Can you see my cursor? Yeah. And so this is after whiten. So after whiten, presumably the lower order statistics is no longer there. Okay, it has only third and higher order statistics. So you're right. And so for each pixel, it has this kind of Gauss distribution which is non-Gaussian. This is the Gaussian, and that's non-Gaussian. Kurtosis is very high, 12.7. If it's Gaussian, kurtosis should be only equal to 3. Okay, so from this measure, indeed, it's very high. And you can also look at these after whitening between 2 pixels. This is pixel number 1, pixel number 2. Between 2 pixels, they are no longer correlated up to second order, which is right. But however, if you go to like a conditional probability, you can review they are still correlated in a higher order. Yeah. So you're right. From these kind of views, it looks like a very, very non-Gaussian. You're right. However, kurtosis and these kind of a moment calculation is one way of looking at non-Gaussianness. Another way of looking at non-Gaussianness is actually simply calculate redundancy. Okay, so do I have it next? Redundancy. Okay. Next. So, okay, how much redundancy is in higher order? So here has only higher. Another thing very important, okay, is higher order. Then you say the first, if you look at just 1 pixel, the entropy is 3.4 bits. This is after you already discretize these gray values in a whitened image into 64 equal size bins, which is 6 bits, all the way to 6 bits if it's equally distributed. However, each of this is only 3.4 just because it's not evenly distributed. It's not histogram equalized. That's not a problem. 1 pixel is like that. Now you can calculate joint 2 pixels. So let's.
Pixel entropy is about 3.4 bits. Okay. So now let's look at the joint entropy of 2 neighboring pixels. If they're completely correlated, they should be about the same as twice that. And so now this is 6.64 bits. So it's already twice that. We can calculate the redundancy, and this redundancy really is less than 3%.
So in that sense, it's very small redundancy. But they say redundancy, let's compare it to the lower order redundancy, okay?
So it's actually a small percentage. Now this redundancy includes only the higher order redundancies because by then the lower order is already removed. But let's look at the lower orders. In the original image, we can do exactly the same thing, but take this pixel value S before the whitening, and we find that for exactly the same grayscaling discrete values of 64, you have, this is the single pixel entropy and neighboring 2 double pixel entropies. And look at this, this is not the twice of that. So additional pixel does not add much more entropy. So because there's lots of redundancy, yeah, so the joint entropy is not much higher, and the redundancy is almost 50%. And so therefore, from this, one can conclude the higher order redundancy is relatively negligible compared to the lower order redundancies, which we more or less removed by whitening.
So what that means is lower order redundancy is Gaussian. Okay, so therefore a Gaussian approximation as far as redundancy is concerned is a very good approximation. And so because our objective function is achieve mutual information, that's again is in terms of redundancy and the information bits, it's actually not too bad. So that's the first thing. Second thing is you can see that these higher order redundancy actually contains all the essential informations. Okay, the lower order, has all the essential information of pepper in there, and so this is what's said next.
It's hard to imagine that the brain would want to build a huge V1 just to remove this small residual amount of redundancy. And this also shows that although visual inputs are obviously not Gaussian, but if one measures the input statistics by entropy, then the Gaussian approximation of visual inputs is not a bad approximation. We can notice that this image has all the essential information about the visual objects in the original image. Meanwhile, we can make another image. This is made by Fourier transforming the original image and then randomizing all the phases in these Fourier waves and do the inverse Fourier transform. And just by doing that, all the essential information about these objects are gone. Now, however, because this image has the same Fourier amplitudes as the original image, then all the first or second order correlations between pixels are the same as this. And from this, we see that the essential information about visual objects are contained in the higher order redundancies, but not in the lower order redundancies. So therefore, perhaps it's a good idea to keep these higher order redundancies rather than removing them, even though this keeping them is for the purpose of object recognition rather than for efficient coding.
Yeah, so that's the idea. So of course, this is going beyond efficient coding. That's something I'm going to talk about. That's the last session. So this is probably a long answer to, is Gaussian a good approximation? And for the same reason, we also want to say, what if we don't do the Gaussian? Would that, this is why we have this alternative way where we do not have to assume Gaussian. Would that solve our problem? That's also not solved. Yeah. Thank you, Curtis. Yeah.
Thank you. Very, very interesting. Thank you.
Thank you. Thank you. Anybody else?